Here is a curve, and one special place on the horizontal axis. Call it A. I'm not going to ask what the curve does exactly at A. I'm going to ask something gentler. As I slide toward A, where is the curve heading? Watch a point right along the curve, creeping in from the left. As its input inches toward A, follow the dashed line across. The height is closing in on a value up here. Call that value L. Now come in from the other side, from the right. Same story, the height settles toward that very same L. When both approaches agree, we say the limit of the function as x approaches A equals L. Let's read this notation slowly, because every piece earns its place. The limit of f of x as x approaches A equals L. In plain words, whenever x is very close to A but not equal to A, the output f of x is very close to L. A sum close as you could ever want just by getting x close enough. And here is the idea that trips everyone at first. A limit describes what happens near A, never what happens at A itself. Notice the words in the corner. X not equal to A. The single point A is deliberately ignored. So at the single point A, the function is free to do three different things. It might be undefined there, it might be defined and equal to L, or it might be defined but sit at a completely different height. The limit does not care. It only reads the neighborhood. Time for the picture that makes limits click. Take this function, x squared minus 1 all over x minus 1. Try to evaluate it right at x equals 1 and it falls apart. The top becomes 0, the bottom becomes 0, and 0 over 0 is not a number. So at x equals 1, the function is simply undefined. But look at its graph. Everywhere, except x equals 1. This is just the straight line. And at x equals 1, there's a single missing point, an open circle, a tiny hole punched right out of the line. Now do the limit thing. Slide in from the left, slide in from the right, and both sides march straight toward the height 2, the very spot the hole sits at. The function never reaches it, yet it's unmistakably heading there. The algebra confirms exactly what the eye saw. Factor the top. X squared minus 1 is x minus 1 times x plus 1. Since x is near 1 but never equal to 1, that x minus 1 on top and bottom is non-zero, so we cancel it. What's left is simply x plus 1, and x plus 1 at x equals 1 is 2. There's our limit 2, matching the whole precisely. Cancelling didn't cheat. It revealed the value the function was aiming for all along. If a picture convinces the eye, a table convinces the calculator. Let's watch the same limit numerically. Feed in x values closing on 1 from each side, and read off x plus 1 from below. 9 tenths gives 1.9, 99 hundredths gives 1.99, 3 nines gives 1.999. Every step, the output crawls closer to 2 from underneath. From above, the mirror image. 1.1 gives 2.1. 1.0 gives 2.0. The output squeezed down toward 2 from the top. Both columns are hugging the same number, left side climbing up to 2, right side dropping down to 2. They meet in the middle, and that agreement is the whole point. The limit is 2. So far, both sides always agreed. But they don't have to. To handle each direction on its own, we use one-sided limits. The little minus means approacher from the left, using inputs below A. The little plus means from the right, using inputs above A. And the rule that ties them together is beautifully strict. The two-sided limit exists only when both one-sided limits exist and are equal to the same L. If the two sides disagree, the ordinary limit simply does not exist. Picture a graph that jumps. Coming from the left, the function rides along the height 1. Coming from the right, it rides along the height 3. At A, it leaps straight up. A cliff in the graph. So the left-hand limit is 1. The right-hand limit is 3. They disagree, 1 is not 3. So the two-sided limit at a does not exist. There's no single value the whole graph is heading toward. There's one more direction to look, not toward a point, but toward the far horizon. What does a function settle into as x grows without bound? First, a warning. Infinity is not a number. It's shorthand for growing endlessly. Take 1 over x. Push x out to the right, 10, 100, 1000, and 1 over x shrinks. Not 0.1, not 0.01, not 0.01. The curve flattens, hugging the horizontal axis but never quite touching it. That flat line it approaches is called a horizontal asymptote. In limit language, the limit of 1 over x as x goes to infinity is 0. Asymptotes needn't sit at 0. Consider to x plus 1 over x plus 3. When x is enormous, the little plus 1 and plus 3 barely matter. The function behaves like 2x over x, which is 2. So this curve flattens toward the line y equals 2. The limit, as x runs off to infinity, is to the ratio of the leading coefficients. 3 worked examples, easy to hard. First, the friendly kind. The limit as x approaches 2 of x squared plus 1. This function is smooth and unbroken. No holes, no jumps near 2. For such continuous functions, you may simply substitute. 2 squared is 4, plus 1 is 5. Done. Second, a trap in disguise. The limit as x approaches 3 of x squared minus 9 over x minus 3. Substitute 3 and you get 0 over 0, the indeterminate form. But 0 over 0 doesn't mean no answer. It means do more work. Factor the top. X squared minus 9 is x minus 3 times x plus 3. The x minus 3 cancels, leaving x plus 3. Now substitute safely. 3 plus 3 is 6. The limit is 6. Third, 1 over x minus 2. A function with a vertical wall at x equals 2, where the denominator hits 0. Watch the two sides behave completely differently. Just left of 2, x minus 2 is a tiny negative number, so 1 over it is a huge negative. G of 1.9 is minus 10. G of 1.99 is minus 100. The left-hand limit dives to minus infinity. Just right of 2, x minus 2 is a tiny positive, so 1 over it is a huge positive. G of 2.1 is 10. G of 2.01 is 100. The right-hand limit soars 2 plus infinity. Minus infinity on one side, plus infinity on the other, as far from agreeing as possible. So the two-sided limit at 2 does not exist. Your turn now. Here's a limit. As x approaches 2, x squared minus 4 over x minus 2. Substitute and you'll hit 0 over 0. So it needs a little work. Pause the video, try it, then come back. Here's the walkthrough. The numerator is a difference of squares. X minus 2 times x plus 2. The x minus 2 cancels against the bottom, leaving x plus 2. Then substitute 2. 2 plus 2 is 4. The limit is 4. If you got that factor, cancel, substitute, you've got the core move of this whole topic. Trap 1. Confusing the limit with the function's value. The limit can exist even when f of a is undefined or sits somewhere else entirely. Always read the neighborhood, not the point. Trap 2. Forgetting the two sides. A two-sided limit exists only if the left and right limits both exist and match. At jumps and vertical walls, check each side separately. Trap 3. Giving up at 0 over 0. That's an indeterminate form, a signal to factor and cancel, not a dead end. There's almost always a real answer hiding underneath. And trap 4. Treating infinity as a number. Writing a limit equals infinity just says the values grow without bound. There's no finite answer, and 1 over 0 stays undefined. Let's lock it in. A limit says where f of x is heading as x approaches a, reading only the neighborhood, never the single point a itself. It exists precisely when the left and right approaches agree on one value, disagree, and the limit does not exist. And two techniques carry you far. At 0 over 0, factor and cancel. Heading to infinity, look for the asymptote. Hold those, and limits will feel less like magic and more like reading a road ahead.